He's a postdoc in astronomy department. And then he's going to talk about the dynamical evidence of the spiral arm driving planet in a MWC 758 protoplanetary disk. Take it away.
Okay, can you guys see my screen?
Oh, yeah.
Okay, great. So I'll get started. So my topic is on spiral arm motion. And the first thing is, of course, what is a spiral arm? So here is a gallery of the spiral arms that have been discovered by the sphere instruments on the Very Large Telescope. And they are in protoplanetary disks. So the first question when people see these spiral arms is to ask, what is causing them? So one of the classical explanation is, hey, there is a planet, and here is a simulation that is based on hydrodynamics, and you will see that in this simulation that the planet is driving two spiral arms. But the problem is none of these planets have been confirmed. And so this is the problem. And in fact, the occurrence of spiral arms around young stars is roughly 20%. But the spiral arm drivers that are massive, so these spiral arm drivers are expected to be giant and young planets. And from the Gemini planets imager, we know that the occurrence rate of such planets is 10%. So there is a problem. But what if the spiral arms drivers are real? So then they will probe such a parameter space. So this is a mass radius. This is a mass period plot. I believe people have seen it a lot. And here are the solar system planets. And when you look for the mass and location of planets that are expected to be in theory, they are here. So actually, when you find a spiral arm system or a ring system, then they're probing the long orbital period parameter space, and that is the new parameter space in studying exoplanets. Specifically, giant and long orbital period planets will dominate the angular momentum in mature planetary systems, such as our Jupiter. So what should we do for spiral arms? So in fact, there are two leading theories in terms of how spiral arm form and thus move. Here is a simulation. So on the left, that will be a planet is driving the spiral arms, and on the right, that is nothing is driving the spiral arms, and the spiral arms are formed purely through gravitational instability. And how do they move? So in the left scenario, the entire system will move as a solid body, and the motion rate will trace the location, or it will trace the angular speed of the hidden spiral arm driver. But in the gravity-induced scenario, then the closer the particles are, the faster they move. And as a result, when you observe the spiral arms in long enough, you will see that they will have distinct motions. So then what we did is that we obtained, so people have obtained the system in 2015, and we proposed observation and get the data in last year. And the first thing, at first glance, you will see that the morphology probably didn't change too much, but the brightness is changing a lot. So actually, we are seeing something that is hidden behind the chronograph. So that is inaccessible, but there is something there. And when you compare the color, when you compare the intensity of the images by dividing them, you will see that the southern part is brightening by a factor of 2 or 4, while the northern part is dimming by a factor of 2 or 4. So there is something happening over here. And what is more, there's similarly some clump that's migrated outwards, and here is the general picture. So let's go back to the topic of spiral arm motion. So what we did is that we fit the location of the spiral arms, or we fit the bone of these arms. And then we look for the evidence of motion. So as I mentioned before, there are 2 formation mechanisms. And in the first mechanism, that's gravitational instability induction. And the expected motion is when you are closer to the star, the azimuthal motion will be bigger. And based on this analytical relationship, we are able to fit the data at the 2 epochs. Although at the first sight, you might say the fit is not bad, but these motion rates will correspond to central star mass. And we found out that if the spiral arm system is actually moving in this way, then the star mass will be only less than 5% of solar mass, which is impossible, which is also a factor of, an order of 2 less massive than what we expect for this system. So what about the other scenario? So the other scenario is that there is a planetary driver that is driving both spiral arms. Of course, they can also both spiral arm can move at distinct rate, but I'm talking about a single planetary driver here. And in this way, no matter what the radial location of the spiral arm particle, the azimuthal movement will be the same between the 2 epochs. And what we found? We found that no matter if we fit them separately, fit the 2 spiral arms separately or together, they are all consistent with co-moving at a rate of 0.22 plus or minus 0.03 degree per year. And this corresponds to semi-major axis of the planet that is located at this contour, with the solid line being the best fit, the dashed line being the 1 sigma region, and the dotted line being the 3 sigma region. And now we can say with confidence that there is a spiral arm driver, and we should look for this spiral arm. So let's step back and look at the big picture here. So for all these spiral arms, we have known that the occurrence of them is a factor of 2 different than the occurrence of spiral arm drivers or giant planets. And therefore, they are not all spiral arms are driven by planets. And by the case study that I showed in the previous slides, we know that we will be able to probe the true occurrence of planets when you see spiral arms in protoplanetary disks. And as a result, we can also perform direct detection for the spiral arms through high contrast imaging. And once we detected them, we'll be able to study their atmosphere using spectroscopy. And that's all my talk.
Great. Okay, great. Yeah, thank you very much for nice talk, Beam. So, yeah, if you have a question, just type in Slack channel. And then before just waiting for other people's question, I'm gonna ask you a question as a chair. So actually, yeah, planet is actually play an important role in the disk structures, right? And then sometimes they generate a spiral and then sometimes a gap. And then what's the main difference to generate the two features?
Oh, that's a good question. So so when you see this image, I'm talking about giant planets. So the major difference is that if a planet wants to excite spiral arms, it has to be very massive. So in current theory, the planet has to be between 5 and 10 Jupiter mass to generate to excite spiral arms. But for the ones that are generating rings, they can be less than 1 Jupiter mass. And from this distribution of the theory, the planet either arm drivers or gap openers, you will see that the arm drivers are more massive than the gap openers.
I see. Okay. But then do you expect that some disk properties like turbulence alpha, what do you think affect the estimate a lot? Or?
Yeah, so for turbulence alpha, I think it's mainly mentioned in the gap openers, and usually from the alpha parameter from 10 to the minus 2 to 10 to the minus 4, the mass of these gap openers will vary by at most roughly a factor of 4, and they're still not so massive as spiral arm drivers. And unfortunately, we haven't imaged any of these spiral arm drivers, planetary drivers yet.
I see. Okay. So, is there any more questions or comments? Yeah, if not, maybe also what's your next step? Definitely, I guess it's better to directly image the planet for these, these objects, right? So maybe H alpha might be a good strategy, or just direct imaging method is good enough, or?
Yeah, that could be. So in terms of this specific system, so in my current estimation, if we use CAC NERC2 in M band, it will take 2 whole nights to image this planetary driver. But before then, we can try to image these spiral arm systems and measure their motion, and to tell, hey, which system should we focus on? For example, for MWC 758, it will take 2 whole nights, and we probably don't need to spend so much time, especially if it turns out that the motion of some spirals is not consistent with being driven by spiral arm, being driven by planets. So the immediate goal that I can envision is to re-image all these spiral systems and track and tell what is the true fraction of spiral arm drivers. So if we can re-image the system in 2021, 2022, then there will be a 5 plus or minus 1.5 years to get a 5 plus or minus 1.5 years of separation to re-image these spirals, and that will be sufficient enough to tell which mechanism is driving the formation or is being responsible for the formation of these spiral arms. Then we can perform targeted imaging for these spiral arm drivers and consequent atmospheric characterization.
I see. Oh, cool. It's really nice. So let's thank the bean again.
Thank you.